Two important developments that questioned the rationality of Bohr's model are: 1. Dual behavior of matter, and 2. Heisenberg uncertainty principle. Let's understand these developments in detail. After the dual behavior of electromagnetic radiation was known, de Broglie proposed in 1924 that all matter has wave and particle-like properties. His theory implied that just like photons, every moving object, be it an electron, a ball, or a planet, has a wave nature. He also gave the relation between wavelength and momentum of a material particle based on the energy equations of photons in their wave and particle forms. A photon displaying wave character has energy equal to h multiplied by nu. A photon having a particle character has energy equal to m multiplied by c raised to the power 2. By combining these two equations and replacing nu with c by lambda, we get lambda is equal to h divided by mc. To generalize the equation for any material particle, c, the velocity of light is replaced with v, the velocity of the material particle. The resultant equation is called de Broglie's equation. Since the momentum of a particle is the product of its mass and velocity, the relation between wavelength and momentum of a material particle can be given by de Broglie's equation. It can be noted from de Broglie's equation that the wavelength and mass of an object are inversely proportional. That is, that the wavelength of heavier objects is small and vice versa. Thus, the wavelength of lighter particles like electrons can be measured experimentally, whereas that of heavier objects like a ball or a planet cannot be detected. De Broglie's theory and equation was later proved to be correct when it was found that an electron beam undergoes diffraction, a property that is unique to waves. The wave nature of electron forms the basis of an electron microscope that achieves a magnification of about 15 million times, and is therefore a powerful tool in modern scientific research. Let's now look at the Heisenberg uncertainty principle. In 1927, a German physicist, Werner Heisenberg, took forward the concept of dual behavior of matter and radiation to give a principle about the uncertainties in simultaneous measurements of position and momentum of small particles. He proposed that it is impossible to measure simultaneously and accurately the exact position and momentum of a small particle like an electron. Mathematically, Heisenberg's uncertainty principle can be expressed with the equation delta x multiplied by delta px is greater than or equal to h divided by 4 pi, where delta x is the uncertainty in position and delta px is the uncertainty in the momentum of the particle. This equation can also be expressed in terms of mass and velocity of the particle. Note that the uncertainty in the position and velocity are inversely proportional to each other. This means that if the position of the electron is known with high degree of accuracy, then the velocity of the electron will be uncertain and vice versa. Also note that the uncertainty in the position and velocity are inversely proportional to the mass of the object. That is, uncertainty in the position and velocity decreases as the mass of the object increases, and vice versa. For example, if the uncertainty principle is applied to a macroscopic object, an object weighing a milligram 10 to the power 6 kg, the value of the product of delta V and delta X is extremely small. Therefore, the associated uncertainty is also insignificant. On applying this uncertainty principle to a microscopic particle, like an electron having mass equal to 9.1 multiplied by 10 to the power minus 31, we find that the product of delta V and delta X is significant enough and therefore cannot be ignored. Hence, we see that Heisenberg's uncertainty principle also holds significance only for motion of microscopic particles and not for macroscopic objects. The position of an electron can be determined experimentally by illuminating it with electromagnetic radiation having a wavelength smaller than the dimensions of an electron. However, the velocity of an illuminated electron cannot be detected as the high momentum photons of the light increase the energy of electrons by collisions. As we have already calculated that for an electron, the product of delta X and delta V is found to be equal to 10 raised to the power minus 4 square meters per second. Therefore, the uncertainty in velocity can be calculated by substituting the value for delta X, say 10 to the power minus 8 meters, in the Heisenberg's equation. This means that if one tries to find the exact location of the electron to an uncertainty of only 10 to the power minus 8 meters, the uncertainty in velocity becomes positive and enormously significant. This value of uncertainty in velocity is so big that the classical picture of electrons moving in Bohr's orbits becomes unrealistic. As it is impossible to determine simultaneously and accurately the position and velocity for an electron at any given instant, it is not possible to talk about the trajectory of an electron. Thus, Bohr's model not only ignores dual nature of matter, but also contradicts the Heisenberg's uncertainty principle. Due to these inherent weaknesses in the Bohr's model, a need for such an atomic model arose which could account not only for the dual nature of electrons, but also be consistent with the Heisenberg uncertainty principle. This search led to the advent of quantum mechanics.